to Physics 11, Kinematics, Lesson 5, Constant Acceleration. Just like with the velocity, the acceleration we use is always going to be an average acceleration because instantaneous still needs calculus. We still have a delta t on the bottom of a fraction, and for that to become zero, we still need calculus. Just like with position and uniform motion, a constant acceleration is always the easiest case. We will not move into acceleration time graphs. We will stop at velocity time graphs. Therefore, any curved motion will be difficult, and we will stick to constant accelerations for grade 11. Constant acceleration is obviously motion where the acceleration does not change, or when the acceleration is constant. On a velocity time graph, this is shown as a straight line. Remember, the slope of a velocity time graph is your acceleration. So if you want a constant acceleration, you will have a straight line shown on your graph. A little less intuitive is a position time graph. In a position time graph, a constant acceleration is shown as a parabola. A parabola is any equation given by the form y equals ax squared plus b, where a and x are any constant number. For example, in these two graphs, you can show constant acceleration. In fact, these two graphs show the same motion of the same object over 4 seconds. Here, this object begins moving at 20 meters per second forward. Over the course of 2 seconds, the velocity reduces and this slows down until at 2 seconds, this comes to a stop. After this object stops, it continues accelerating negatively and it begins to move in the negative direction, slowly increasing speed as it goes, and it gets a larger and larger negative velocity. Similarly, in this question, here, the slope of this line is a very, very steep slope, and it starts with a very high velocity. As it moves over 2 seconds, the slope of this green line reduces, and gradually at 2 seconds becomes 0, where it stops. After 2 seconds, the object turns around and starts to go faster and faster with a more and more negative slope until 4 seconds, and it becomes faster with a more negative velocity. As you can see, these two graphs actually show the same motion of a certain object. The only difference is this is a velocity time graph where the graph is given as a straight line, and this is a position time graph or displacement time graph where the object follows a parabola. Even though these two graphs look very different, they're actually showing the exact same thing, a constant acceleration in the negative direction. As we saw before, finding the acceleration of this graph is simply finding the slope of this line. However, for here, finding the acceleration is finding the change in the slope, which is difficult and requires the use of calculus. So as before, we will stick to the straight line, and when we are dealing with acceleration, we will stick with a constant acceleration looking at a velocity time graph. This is the same situation, but a more complicated graph that requires calculus to solve. But where can we find a constant acceleration? Much like constant velocity, constant acceleration is very difficult to perform. There is one source of acceleration that is constant no matter where you go, and this is probably the most common source of acceleration you will find. This source of constant acceleration is gravity. Gravity is a constant acceleration of negative 9.8 meters per second squared. In fact, if there was no air on Earth, everything would fall at the same rate. All objects, whether it be a hammer or a feather, would accelerate downwards at 9.8 meters per second squared. The only reason why this does not happen is because Earth has an atmosphere and it has air that gets in the way of the feather more than it does for the hammer. If you were to drop a feather and a hammer on the moon, they would both hit the ground at the same time. This was a theory first proposed by Galileo a long time before people could actually travel to the moon. In honor of Galileo, the NASA astronauts who first went to the moon brought with them a hammer and a feather, and they actually did this experiment on the moon where there was no air. Much like Galileo predicted, both the hammer and the feather hit the ground at the same time when the objects were dropped at the same time. If we have a constant acceleration, there is one new equation that will apply. This equation states that the average velocity given if you have a constant acceleration is simply your final velocity plus your initial velocity divided by 2, where these are all vectors. This equation is only true with a constant acceleration. If the acceleration is changing, this is no longer true because this simple average only works with a straight line. This equation, along with our other equations before, v equals delta d over delta t, and a equals delta v over delta t, can be combined to find two new equations. In this situation, the velocity that is found by finding the displacement over the time interval is actually an average velocity. Because remember, since this t is not zero, this is not instantaneous, it must be an average. Do not confuse the average velocity with the change in velocity. If you find the acceleration is delta v over delta t, this cannot be replaced as delta d over delta t over delta t. This is incorrect because the change in displacement over the time interval is not equal to the change in velocity, it's equal to the average velocity. And here you can see the average velocity is not Vf minus Vi, but Vf plus Vi over 2. So these are two completely different things. So we now have a new equation for a constant velocity. For example, if you drop something. But can we find how far something will fall after a certain time after we drop it? Currently, with the equations we have, we do not have anything that combines everything together. But we can combine all these equations to get a new one. So let's do so. Here, we will begin with our three equations. First, our average velocity is equal to the change in our position or displacement divided by our time interval. We also have our acceleration is equal to the change in velocity over the change in time. And our new equation, the average velocity, if we are under a constant acceleration, is the final velocity plus the initial velocity divided by 2. We will begin with our first equation, v average equals delta d over delta t. We can rewrite this equation to find that the change in our position is equal to the average velocity times our change in time. We know that our average velocity is actually equal to our final velocity plus our initial velocity over 2, which is still multiplied by our delta t. We can take our original acceleration equation and we can rewrite this as our final velocity minus our initial velocity is equal to a times t. Solving for Vf, we find the final velocity is equal to the initial velocity plus at. And we can substitute this value into our new equation. This gives us the equation Vi plus At plus Vi over 2 all times delta t. Here you notice we have a Vi and a Vi. This can be combined into 2 Vi plus At over 2 all times delta t. Using our knowledge of fractions, we know this can be simplified into 2 Vi over 2 plus At over 2 times delta t. This first term just simply becomes Vi plus At over 2 times delta t. Distributing our time into our brackets, we find we get the Vi times t plus At over 2 times t, where we change delta t into t, as we did already before. This shows us that delta d is equal to our initial velocity times time plus half of our acceleration times time squared. In your equation sheet, this is written as d equals Vit plus half a t squared. This d is actually a change in your displacement. You can also write this as df minus di equals Vit plus 1/2 a t squared. And you can take the di and move it to the opposite side of the equation. This equation gives you the final position if you know the initial conditions and the constant acceleration. So rewritten, this equation is now df is equal to di plus Vit plus 1/2 at squared. This will be one of the most used equations in our next unit that deals with projectiles. But let's do an example. If you were to throw a projector outside of the window so it falls down, how far would it be after 2 seconds? In this case, let us begin by drawing a picture. Here we have a building. Outside of this building, we will drop our projector so it begins to fall down. We know we are on Earth, so we know that our acceleration must be minus 9.8 meters per second squared up. We wish to know how far down this will go, So we will say our initial distance is 0, and we are measuring from us. How far from our position will this displacement be? When you drop something, the moment you release that object, the object is actually not moving. For a split second when you let go, the velocity of the object is 0 before gravity begins to pull it down. So you should know anytime something is dropped and you hear the word or read the word dropped in any question or any situation, you should know that the initial velocity will be 0 meters per second. If you drop something, there is no initial velocity. You are simply letting it go from rest. From the question, we also know that time is 2 seconds. So here we have done our second step. We have written down everything that we know. We wish to find our final displacement as the question stated. We can use our original three equations and have a long line of work that finally puts us to the, and have a long line of work that finally takes us to the answer. Or we can use our new equation, df equals di plus vit plus 1/2 at squared, where these are all vectors. In this situation, we know that the di is equal to 0. We know that the vi is equal to 0 times 2, and our acceleration is minus 9.8 times 2 squared. Putting these numbers together, we will find this is minus 19.6 meters up, or in other words, 19.6 meters down. After 2 seconds of dropping something from the window, this object has fallen 2 times 10 to the 1 meters down from wherever you were, assuming it did not hit anything on the way down. Now, in this question, you were given the time, but in real life, you do not often know the time in this situation. If we don't have the time, can we do anything? Are there any calculations that can be done? Well, similar to what we did before, we can combine our three equations and find a time-independent equation, one that does not need time. So as before, we will begin with our three simple equations. We have our average velocity is equal to the change in displacement over the change in time. We have our acceleration is the change in velocity over the change in time. And we have our average velocity is equal to our final velocity plus our initial velocity over 2. Here, as before, we will write delta t simply as t and assume t stands for the duration of time of some event. As before, we will start by combining our two velocity averages equations. Here we can see that the change in distance over the change in time. Here we can see that the displacement over t is going to be equal to our final velocity plus our initial velocity over 2. By cross multiplying, we can see that 2 times the displacement is equal to Vf plus Vi times t. Now we will introduce our last equation. By rearranging this equation, we find that t is equal to Vf minus Vi over A, and we can substitute this t into our new equation. After doing so, you'll find 2 delta d is equal to Vf plus Vi times Vf minus Vi over A. Moving our A to the other side, we find this is 2A delta D is equal to Vf plus Vi times Vf minus Vi. You may remember from math, if we have two binomials, A plus B times A minus B, this leaves us with A squared minus B squared. So similarly here, A is Vf, B is Vi, and we will get Vf squared minus Vi squared. This is still equal to 2AD. Solving for Vf, we have Vf squared is equal to Vi squared plus 2A times delta D. Here we have an equation that relates many variables but does not involve time, as shown here again. So this is an equation that is independent of time, which we call the time-independent equation. Vf squared equals Vi squared plus 2A times delta D. For example, assuming you dropped the projector from the 5th floor, and the 5th floor was 15 meters above the ground, how fast would the projector hit the ground after it was thrown out of the window? In this situation, we do not know how long the projector spent in the air, but we do know the initial velocity, the acceleration, and our change in displacement, so we can find our final velocity. To do so, we will start by writing down everything that we know. Here we know our initial velocity, because we dropped this projector, will be 0 meters per second. Our acceleration, because we are on Earth, will be minus 9.8 meters per second squared up. We also know that because we are starting on the 15th floor, our initial position is 15 meters up, and after we hit the ground, our final position will be 0 meters from the ground. This question wants to know how fast will the object hit the ground, so we are looking for VF. Again, you can start with the three basic equations, combine them until you have an answer, or we can begin at the time-independent equation. Here we know VF squared is equal to VI squared plus 2A delta D. Plugging in the values we know, this is 0 squared plus 2 times minus 9.8 times 0 minus 15. This gives us 294 as our answer. But be careful, this is not our final velocity. This is our VF squared. To find our final velocity, we must take the square root of 294. Taking the square root of this number, we find our final velocity will be 17.146, or given our sig figs, this will be equal to 17 meters per second down. Here, be careful with your direction. You cannot trust the sign of this answer because the square of 294 is actually plus or minus 17.146. To determine whether it is positive or negative, you must analyze this question. If you drop something, after a certain distance, it will be moving down. So logically, this direction should be down, and therefore this was negative 17 up. Given those two new equations, let's attempt three more questions. Consider a ball is falling 44.1 meters. How long has the ball been falling? Here, let's begin by drawing a picture. We have a ball that has fallen some height 44.1 meters. We know that this is on Earth with gravity, and we know that this was dropped, so at the beginning it was not moving. After we have the picture on the paper, let us write down everything we know. We know that our final position is equal to minus 44.1 meters up, assuming our initial position is 0 meters. We also know, because it was dropped, our initial velocity is 0 meters per second. Since this is on Earth, we know our acceleration is minus 9.8 meters per second squared up. From the question, we know we want to find time. Do we have an equation that involves all of these variables? Our displacement equation, which equals di plus vit plus 1/2 a t squared. Here, luckily, our initial conditions are both 0, so these terms actually disappear, and we are left with df equals 1/2 a t squared. Solving for time, we have our time is equal to the square root of 2 times df over a. Plugging in our numbers, we find this is equal to the square root of 2 times negative 44.1 over negative 9.8. Putting these numbers into the calculator, we find that our time is equal to exactly 3. In the question, we have three significant figures, so we must put 3.00 seconds. Our answer is 3.00 seconds. Our next question, how high would a ball thrown up at 15 meters per second be after 2 seconds? So again, let's draw a picture. Here we begin with a ball that is being thrown up at 15 meters per second. We know after you throw a ball up, it will move up and then slow down. The reason why it slows down is because gravity is pulling it down with a certain acceleration. Now that we know our situation, let's write down what we know. We know our initial height is 0 meters. We also know our initial velocity this time is 15 meters per second. Our time is 2 seconds, and our acceleration is minus 9.8 meters per second squared up. Here we should confirm that this velocity is indeed up, and according to the question, it is thrown up at 15 meters per second. We want to know how high the ball goes, so the number we look for is df. So we begin now with our equation. df equals di plus vit plus 1/2 a t squared. This has already been solved for what we want, so we will jump straight to putting in what we know. Our di is 0, so we can cancel out that term. Plugging in everything else, we find this will be 15 times 2 plus 1/2 times minus 9.8 times 2 squared. Do not forget this negative sign. If you forget this negative sign, it will completely change your answer. Putting these numbers into a calculator, we find our height is 10.4 meters. For our last question, let's look at a car. If a car accelerates at 50 meters per second squared from stop, how much road does it need to reach 100 meters per second? So again, for this question, let's begin by drawing a picture. Here we have a car initially at rest that accelerates until it reaches 100 meters per second. Since it is at rest, we know it starts at 0 meters per second, and we want to know how much road does it need to get up to that speed. So let's write down everything that we know. We know our initial velocity is 0 meters per second. We know our final velocity is 100 meters per second forward. We also know that our acceleration is 50 meters per second squared, also forward. And we want to know how much distance do we need to get to this high speed. Here, you may notice we have nothing to do with time. So we're going to guess that we need to use the time-independent equation as shown here. Solving for d, we find that d is equal to vf squared minus vi squared over 2a. Plugging in the numbers that we know, this is equal to 100 squared minus 0 squared over 2 times 50. This gives us 100 times 100 over 100, which is equal to 100 meters. So the distance we need to get up to speed is 100 meters, or with proper sig figs, 1.0 times 10 to the 2 meters. Make sure you are comfortable with these equations and confident in your ability in them, because these equations form the backbone of our next unit, projectiles. If you are not able to use these equations well, you will not succeed in the next unit dealing with projectiles. That is all for constant acceleration. Thank you for watching.